All right, welcome everyone to the fourth talk in our summer Chilloquium, co-organized by Harvard and MIT Society of Physics students. My name is Tung, and I'm an undergraduate studying physics at MIT. I'm one of the organizers of our Chilloquium speaker series. I'm here today with my co-moderators, Jennifer and Kwon, and we are very honored to have Professor Eun-Ah Kim from Cornell University to speak with us today. If you have questions at any time, you can raise your hand in the Zoom participants sidebar, and we will call on you. Or you can privately send a message to me, and I will ask for you. We will prioritize those who raise their hands in order to make our events feel as conversational as we can. In the spirit of keeping this a more relaxed and personal conversation, we also request that everyone be muted unless they're speaking, and also have their video on if they're willing and able. Now, before starting the talk, let's briefly introduce today's speaker to you, Jennifer.
Thanks, Tom. We're extremely excited to have Professor Eun-Ah Kim give us a talk today. She is a condensed matter physicist and professor at Cornell University. Her research revolves around the theory behind strongly correlated systems, including high-temperature superconductivity, electronic liquid crystals, and topological phases. She is an expert and pioneer in applying neural network-based machine learning to her work in understanding these phenomena in condensed matter systems. Thank you very much, Professor Kim, for giving us a talk at Chilloquium this week.
All right. May I get started? Okay, great. Thank you for the invitation. I'm really honored to be here. So I want to talk about learning quantum emergence from quantum matter data. But I would normally just move on to motivation, but I was told that this is a special kind of format and you would like to humanize those of us who are professors. So I thought I would give you some glimpse of my life. These are people who are very important to me professionally. This is my research group. We got together during March meeting because I've been on sabbatical leave at Harvard and I haven't been with the group members in person for a while. And this is my family, also very important people in my other side of life. We took this picture during a conference last summer in Valencia. So this is a picture from my 5th grade. I'm from Korea. In Korea elementary schools, we do this like sports activity where there are various performances and so on. And around this time, what I was thinking was that I was really interested in science and I was really interested in electricity and magnetism, phase transitions, melting of ice. These things were fascinating to me. But at the same time, I started to ask questions about, can I have it all? I think men typically don't ask such questions at such a young age, but I was starting to hear from my mother's friends who said, either girls would lose out to boys when boys start to catch up, or no boy would ever want to have a girl who's smarter than them. So such comments started to make me wonder, is it possible for me to have work and life? That was the kind of questions that bothered me. This is a picture from when I was graduating from college. So I understand many of you are undergrads and you will have a graduation. And this is my picture from graduation in 1998. By this point, I have learned what emergence means from StatMech and thermodynamics, and I found it to be extremely interesting. But at the same time, I was asking myself, in this very competitive world full of really smart people, will I make it? And I guess I have made it in a way. My definition of making it is having the resources and support to pursue the research that interests me, and having the opportunities and blessing to work with brilliant people, having friends that I can collaborate with, and always being surrounded by talented young people who energize me and I learn from them. Now, my history from after graduating from college was to go through 2 years of master's degree in Seoul National University. And I did research in, my thesis topic was phase transitions in coupled charge density wave systems. And I still study charge density wave systems. From 2000 to 2005, I did PhD at UIUC with my, and my advisor, PhD advisor was Edward Fratkin. And I did mostly pencil and paper field theory work studying edge states of quantum Hall systems as a way of probing exotic properties of anyons in quantum Hall states. 2005 to 2008, I was a postdoc at Stanford Institute for Theoretical Physics. And I kind of switched my research topic from topological phases of quantum Hall systems to high TC and strongly correlated systems. My rationale for the transition was that I wanted to have more breadth. Quantum Hall states are extremely interesting. Topological phases are interesting because you get to play with fascinating math, mathematical formalisms, and study wild possibilities. And there is some connections to real systems, and there is this excitement coming from being able to connect extremely beautiful mathematical formalisms and language to something that might be observable. But at that time, by 2005, quantum Hall, this was before topological insulators. So quantum Hall systems were essentially the only topological systems. And the only way quantum Hall systems were studied was through transport. And I found having only one way of, essentially one way of studying a system rather limiting. And I had a hunger and desire for learning broader set of phenomena and broader ways of probing interesting physics. So when I was starting my postdoc, I decided to switch the topic and study strongly correlated systems and high TC superconductivity. So starting from 1998, when I was graduating and still not sure whether I will make it, this is the path that I went through. And in 2008 September, well, August, I started at Cornell as an assistant professor. Although I started at Cornell as an assistant professor in 2008, I think I started to understand who I am as a researcher much later. And answer to, can I make it, also much later. Although from some perspective, starting an assistant professorship at a wonderful university as Cornell sounds like making it. It's all a matter of your definition. But I had not shaken off this feeling that, am I really worth it? Like, do I know what I'm trying to do? The question that scared me the most was the following question: what is your expertise? People ask such a question, what is your expertise? And I didn't necessarily know how to answer that. People would ask, what is your strong suit? I didn't exactly know how to answer that. So very soon I'm going to switch gears and start talking about my research and what I'm really excited about, starting with the background. But if there is one sort of secret that I could share with you, if any of you are asking the question that I asked as a junior and senior, will I make it? If you're asking such a question, I want you to think about the first question here, what is your expertise? As really asking what is your strong suit. And if you don't necessarily know how to answer what is your strong suit, I want to invite you to think about what comes easy for you. For me, it took me a while to understand that what is easy for me is not necessarily easy for everybody else. Not easy for everybody else. So what is easy for me is my strong suit. That's reflection of my talent. And starting to understand how can I contribute in an authentic and unique way? How can I contribute to the frontier research in a way that only I can do? I started to understand this in a way that I can articulate for others, which is the answer to these questions. When I started to recognize that what is easy for me is my strong suit, and that is going to determine my expertise. I can go from bottom up. And we are all very different. So when you can figure out what your special sauce is, what is your magic for you, then you can start to use what makes you special to answer the question the world wants to know. Once you know who you are and who the world is, that is what the frontier research needs answered, then you can start to find how can you answer frontier questions in a way that is competitive because you're doing something that you're especially good at. All right, so let me start talking about emergence. Here is sort of image. Here's a GIF where people are doing a wave cheering at a sports game, and the phenomena that you're seeing is not a reflection of individuals so much as how the individuals are interacting with each other. And understanding one person to whatever depth is not going to explain the phenomena, macroscopic phenomena that we are seeing. And that's an example of emergence. But the problem that I'm interested in, the system that I'm interested in, that is not a system of humans, but everybody has cell phones. You look inside cell phones, there will be atoms and electrons. And it's the collection of electrons that's what I'm interested in. And the emergent phenomena of the interactions and cooperation between these electrons, and that is also determined by the environment they're placed in, can give us wildly different properties. So here there are pictures of two materials at room temperature. This is YBCO, high TC superconductor, and it looks dull. And this is silicon, which is a semiconductor, and it looks shinier. The reason is because the society of electrons inside YBCO at room temperature is very chaotic. It's a poor conductor. However, if you cool this material down, it changes its material property dramatically, where electrons form sort of a lockstep coherent state, macroscopically coherent state, that is superconductor. Semiconductor silicon is like a bridge where you can open or close. It would conduct or not conduct. The transport property of silicon is, or semiconductors are very nonlinear. So these are different types of societies and social phenomena that electrons can form. And I think of study of emergent properties of electrons as studying sociology of electron societies in different environments. Now, what enabled miniaturization of computers from a computer that required a whole building to what fits in our hand was the semiconductor revolution. It's the progress in solid state physics, now called condensed matter physics, that allowed vacuum tube to become transistor. And now the transistors are in integrated circuits on a chip. Now, quest for zero heat loss, trying to conserve energy, has been also pursued in study of quantum matter through studying topological edge transport or high TC superconductivity. So these are vastly different societal phenomena that electron society can exhibit. And what we would like to do, my community would like to do, is to understand and control trillions of individual electrons, that is 10 to the 23. Nowadays, there's also quest for quantum information technology. Instead of working with qubits that are, instead of working with classical bits that are either on or off, that is vacuum tube technology or transistor technology, we would like to work with qubits that have a phase degree of freedom. And electron spin is the most representative way we think about qubits. Although actual qubit technology that we're working with is not single electron spins, but coming up with a macroscopic system such as superconductors that can mimic a behavior of a single spin. In pursuit of trying to understand how to control many electrons, extremely large number of electrons, to see how different societal behaviors can form and how these societies can change in a dramatic way. The community of quantum condensed matter theorists and experimentalists have been always trying to learn from experiments, and that's what makes this subject area studying matter at this scale, which is smaller than astrophysics scale, but larger than that of high energy physics scale. This scale is particularly interesting because we can have experiments happen in the labs and try to understand them in our lifetime or in a matter of months or a year. This study of quantum matter have started to experience data-driven challenges. And that observation prompted me to start learning about machine learning and trying to use them for my research. So tunneling density of states in 1962, this was before most of us, if not all of us, were born. At this time, tunneling density of states were studied through macroscopic tunnel junctions. So here is a tunneling barrier, and if you have superconductors on the blue side, and you measure tunneling current, and you measure the tunneling conductance, what you're going to find is that there is no tunneling through this barrier until the bias is above certain energy scale. And that is what this curve is showing. Until a certain point, there is no conductance, and then there is a peak, very sharp peak. Those of us who are studying superconductor know this curve. This is an important curve, that historically very important curve. We know this curve to our heart. We know that what this suppression means. We know what this peak means, but we also know what these subtler features mean. Being able to model these subtler features gave us confidence that the BCS theory of superconductivity was correct. What do I mean by data revolution? What I mean by data revolution is that over the course of time, we went from having one curve that we try to understand to having 10,000 curves that we want to understand. With scanning probe, instead of macroscopic tunnel junction, we form a tunnel junction with a vacuum layer, and you move the tunnel junction over the surface of the sample, and what you obtain are 10,000 or more tunneling density of states curves. And how do we study such volume and complexity of data? X-ray diffraction. In 1913, this is Nobel Prize winning paper by Father and son Bragg and Bragg. They were interested in trying to understand these three peaks as they change the angle of incidence when the X-ray beams are coming into their sample. And they came up with the very first forward model. That is, you come up with a model with a parameter and try to fit the data and try to simultaneously confirm the correctness of or effectiveness of the model and learn something about the system. That forward model is nothing other than the Bragg condition that you would all have learned from your introductory physics. And the forward modeling model parameter here is the distance between the planes of atoms. Assumption was that the atoms will form plane, and with one parameter, fitting this formula to the positions of the peaks in the angle, they were able to extract measure the distance between the atoms, atomic planes. This obviously was an extremely successful model. We know that it was successful because it's what we teach in introductory physics. But nowadays, instead of 3 peaks, we can have 100,000 peaks because we are working with brighter beams and we have much better detectors. When you have orders of magnitude more information, you should be able to extract more knowledge about the system. But this is at a scale where we cannot approach with conventional approaches that worked for a few peaks. And a few peaks are of interest. Stern-Gerlach experiment, another thing that you would have learned in introductory quantum mechanics. This was the very first projective measurement in 1922. When I was learning quantum mechanics, which I've learned started learning in junior year, I think, it was really exciting. It was just so different from classical mechanics or E&M, and it felt like, although it was so many years later, I could still feel the excitement the contemporaries of Stern-Gerlach were experiencing. And I could not shake off the feeling that I was born too late. Gosh, if we were at this time, we would have been able to make so many discoveries. Lucky for all of us, turned out we are now living yet another really exciting time, because instead of studying projective measurements on one spin, these days we can study, we have access to projective measurements on hundreds of spins or qubits. So quantum simulations, this is image taken from this paper by Lukin group at Harvard. But quantum simulations on various platforms that are available today put us in a very different time than the prior generations, where we can study and manipulate these quantum mechanical systems that are not just one qubit, but a few body, or hundreds, or maybe even hopefully soon thousands. And tangibly study quantum mechanics or quantum many-body physics, not mechanics, but quantum many-body physics. But there is once again data-driven challenge, because the Hilbert space of hundreds of qubits is enormous, and the way we can access all that information of the many-body state is through the partial view of projective measurements. So what I have been pursuing for the last 6-7 years is to expand my scope of being really interested in connecting complex quantum matter data to theoretical insight, to include machine learning as a tool for bridging data with insight, and expanding to include quantum simulators as a way of understanding what are possible behaviors when you have truly many and truly quantum mechanical constituents, in a way that we can prod one and also prod hundreds. The way I think of machine learning is as a tool for learning physics. And of course, here is an example of a tool. It's a handheld drill. You can make a hole with this drill, but you wouldn't want to build a house with such a drill, because what a power drill can do is faster, and speed can matter when you're trying to build a house or have a bigger project. But also it is very adaptable. You can change the drill bits and do many different things. And I think of machine learning strategies and methods as tools, like power tools. And just like it can be overwhelming for someone who to enter a hardware store, American hardware store like Home Depot, if you're first time at that store, it's overwhelming. The scale, the variety, it's overwhelming. Looking at the machine learning methods, algorithms, strategies, landscape can be also overwhelming. Looking at where quantum simulators are, if you're new to that, that can also be overwhelming. However, if you have a clear-eyed view on what you want to solve and how you want to use what is just becoming available, from my perspective, I am very much looking at these new opportunities and possibilities as sort of tools for understanding something that I've always wanted to understand. And for understanding physics, minimalistic approaches that integrate physics principles can be particularly helpful, because my goal is not to develop a better algorithm, that's not my strong suit, but my goal is to understand answer questions that I've always wanted to answer. And I need to be able to interpret what is going on, whether it is a classical machine or a quantum machine. Now, let me give you 2 examples of how I use machine learning to study quantum matter data. First is supervised machine learning for hypothesis testing. This was work was this part of the talk is based on this paper, where we thought to use neural network to recognize motifs in STM data, just like one can recognize different handwritten digits as being associated with abstract notion of numbers. Nobody actually writes 0, 1, 2, 3 in their handwriting identical to some print. But so in a way, we can think of the print as an abstract idea, notion, or theory. Everybody's handwriting is slightly different, but there is some essence to it that connects all of those to a particular essence or theory. And that's the kind of approach we were taking in looking at STM data. So how does supervised learning work? Supervised learning is letting letting machine come to a decision. An algorithm has to come up with a decision. When a kid drops food, the kid has to make a decision what to do with this food. the decision by machine is determined by weights and biases. And this kid will also have to make a decision. Both this kid and the machines that we can work with will take inputs. How long has the food been on the ground? Is mom or the or parent watching? How sweet is food for my kids? The color of the food also is important. So kids will take these kind of inputs, and they have to come up with an output. That's a decision. Now, connecting inputs to output is a function. That's a definitional function. So clearly, making the connection between the set of inputs and a definite output will be a function. In a neural network, that function is represented through hidden layers where the input vector is multiplied to weight matrix and added to a bias vector, and the whole thing goes through a nonlinear function. Different neurons would have different associated weights, coupling it to different input components and different bias. And the output from each of the neurons gets collected with different weight, and that ends up into a decision. So a neural network writes a function, and the nonlinear structure and this layered structure allows us to express complex functions. If I take away all the analogies and abstract out what was just written in the previous slide, it's this function that is being written, and it is being parameterized by weights and biases. The computing before machine learning, the idea was to learn what are the best weights and biases or best ways to write the function, and then write the function. Computing after using machine learning is to try to learn these weights and biases based on the feedback. So how can we use this supervised learning approach for quantum matter research? We have used it to do the hypothesis testing. Neural network, as this very simple neural network that I have illustrated, is best suited for multiple choice questions. But turns out in quantum condensed matter physics, when we are interested in different phases, we are often asking multiple choice questions. So we were interested in asking the following question, given this data, is when we see this kind of pattern formation, modulation, should I think about it from starting from momentum space that is free fermion starting point and think of it as this density modulation forming from so-called nesting, or should I think of it as real space or strong coupling phenomena starting from spins on the copper side and holes in the oxygen side frustrating the spin-spin interaction? And the conclusion we arrived at using machine learning was that these patterns are are most similar to what one would get from strong coupling perspective, because they are best described by lattice commensurate modulations. So and this conclusion was arrived at using simulated data to train neural network for different possibilities, simulations associated with different hypotheses, and letting the neural network that's trained on simulated data call the decision based on the experimental data. Now I'm going to switch gears and give you a glimpse of how we use unsupervised learning for large volumes of data. Here we were interested in trying to find hidden trends in large volumes of data, and you can find more details in this paper. Now, searching in this large space of large number of large volume of data in momentum space here. So each of the cubes are representing 3 momentum coordinates, kx, ky, kz, and this curve is representing temperature evolution. So there is large volume of data being taken because of extremely sensitive detectors and bright beams. And but not only that the data is taken at large volume, the large volume of data is taken as one controls various control parameters such as temperature. So what is increasingly happening in the way we probe quantum matter is that we are gaining higher resolution and more control and larger dimensionality of exploration. You can add temperature, you can add pressure, you can add composition, and the dimensionality of the data is only growing. In that large volume, the what you are interested in may not be everywhere. And in studying the scattering data, such as X-ray or neutron, or transmission electron microscopy, what is really difficult is searching for the peak or searching for something interesting in that large volume. Just like searching for a special piece in a pile of Lego. When you are given a task as a pandemic parent, having to find that special piece that your kid just really needs right at that moment, and being asked that day after day, you quickly learn what you don't want to do is to pick up one piece at a time and inspect it because you get tired. As humans are really not really designed for repetitive tasks. We just lose attention, we get bored, and just miss. We start to lose attention and we start to miss what's right in front of our eyes. So we quickly learned that, if I am asked to find a specific piece, I should sort of think of a larger category and try to sort. If I'm asked for a particular color piece, I should start by sorting by color. If I know shape, I should sort by shape. So can I use this kind of strategy for large volumes of X-ray data? I need some criteria. Color or shape is not what's going to work. But we thought maybe what we can use, and we wanted to develop a tool that is broadly useful. We realized that we are always interested in how the energy and entropy are competing, controlled by temperature. So we want to look at how the data evolves as a function of temperature. And this is really a very different perspective than the conventional way these data have been analyzed. People try to understand each peak because trying to understand all peaks is impossible. We cannot have graduate students sitting there working on it for that long a time on one set of data. So people will select a few peaks and then study it really carefully. What we wanted to do was to look at all the data and look at all the data as and observe how it evolves as a function of temperature. And this is not something that you can do with a manual inspection. But with computers these days, this is not a hard task. If you know how to frame the problem in a way that can be done with a computer. So we thought of looking at each X-ray intensity at a particular momentum space position as a function of temperature, the whole temperature evolution as a series. And then that defines a high dimensional space. If I have 15 temperature points, I have a 15 dimensional space. If the temperature evolutions are different for different types of phenomena, we expected to see clustering in this space. And what are different phenomena that you could be interested in with X-ray data? The system could be in a fully symmetric state, but it can go through different symmetry breaking, such as charge density wave that is changing the periodicity, or intra-unit cell order, which does not change the unit cell size or periodicity, but changes symmetry inside the unit cell. Charge density wave, which changes the size of the unit cell or periodicity, gives new peaks. And these new peaks signifies that there is charge density wave. Intra-unit cell order is subtler because there is no new peak showing up. What is showing up is change in the form factor, which is observable when we look at multiple Brillouin zones. Fluctuations are even subtler because they don't present themselves as sharp peaks, but it's sort of a diffuse phenomena. And these are all things that are in the data. The particular problem we were interested in is that of pyrochlorocadmium renate, which is a material that goes through structural transition before you finish. Yes? Mm-hmm.
Yeah, I'd like just to quickly remind that there is 5 minutes left until the Q&A session.
Mm-hmm. Okay.
Right. Yeah.
Good. So the material goes through different structural transition before it becomes superconducting. And with the approach, unsupervised learning approach we developed, we were able to process 8 terabytes of data in 10 minutes. Out of this collection of raw temperature series, we discover there is a cluster that shows clearly ordering phenomena. You lower temperature, intensity goes up, and then there is a background. And from the comprehensive analysis of data, we were able to learn the particular way in which there is displacement, and we were also able to learn fluctuation between 2 modes in this 2-dimensional order parameter. So these are just sort of sampling of how we can use machine learning, supervised and unsupervised, to gain new insight into complex data and accelerate discoveries. In remaining probably 4 minutes, I want to give a quick glimpse at how we are now using programmable quantum simulators, that is quantum machines. This part of this is a sort of a research direction that is bringing me back to my PhD interest, that is trying to study topological states and anyons. Now, what we were able to do in a recent theory that guided the experimental work at Google was to realize non-Abelian statistics using on a quantum processor guided by graph gauge theory. Now that's already a lot of words, and I know in this short period of time, I have sort of spent kind of broad selection of topics, and there were many different new vocabulary possibly for some of you, or I don't know, many of you. So in remaining couple of minutes, I'm not going to go into what non-Abelian statistics are. I'm not going to go into what graph gauge theory is, and I'm not going to try to explain what quantum processors are. But I want to just share a little movie that shows the core excerpt of how we were able to realize non-Abelian statistics. So here is a video. Let's see. Okay. So I'm starting with 10 qubits. I represent it with Lego bricks because for this geometric view, it's enough to think of them as toy pieces. And these lines are representing how we are defining the 10 qubit state. So this qubit has 3 lines emanating from it. That makes it degree 3 vertex of a graph. And this qubit has 4 lines emanating from it. So it is degree 4 vertex. In this view, we already have 4 non-Abelian anyons. These qubits that have degree 3 connections are non-Abelian anyons. I I don't have time to explain why they are non-abelian anyons, but what I'm going to show is how we move these anyons without moving the qubits. So we start with qubits, these lit ones being anyons, just because these lines were removed at time t equal to 0. And now I'm going to start moving this qubit in by moving the edge. So now this qubit have 4 connections, and this qubit has 3 connections. So that's where the anyon is. Now I swing another edge. Now this have 4 connections. Therefore, my anyon moved to this location. My goal here is to swap 2 anyons that were on this side and this side. And that would be a braid that is twisting the space-time trajectory of anyons. And we are accomplishing this by moving the anyon location through the edge swinging moves. What you're seeing in front of your eyes right now is totally classical. This is geometry, how we can manipulate the graph. Figuring out how to translate this geometric information to control of qubits and what is the state that you're realizing is where the graph gauge theory enters. But what I have just demonstrated is how the anyons were actually braided in this recent experiment. Going through a step from T1 to T8, these 2 anyons were exchanged, their positions were exchanged. When you do that twice, everybody returns to where they were at the beginning. For classical particles, nothing would have changed. Abelian anyons might have gained a phase, but for non-abelian anyons, that double braid changes the state of logical qubit that these 4 anyons were representing. So doubling this braid that I've just demonstrated amounts to logical X gate. So with that, let me just end with, I guess I should stop sharing screen. Okay, I have just one last slide. Let's see. Sorry. Let me go into presenter view. Yes. Okay. So this is a scene from a movie that I really enjoyed called Hidden Figures. These are human computers who were doing calculations for orbits of the NASA or space program before machine computers were introduced. Just about the time when machine computers started to become useful. Classical computers, IBM 7090 was introduced in 1961. Many of the human computers lost their jobs, but these human computers had the vision to learn to program the new computer that is arriving. And they transitioned from being computers to programmers. Today, we are really fortunate to be living at a time where revolutionary progress is being made in the world of classical computing and also in the world of quantum computing. And what I want to invite you all to is taking an adventurous view of trying to learn what are new opportunities and trying to find ways in which that you can contribute, but all from the vantage point of knowing who you are, what is your strength, what is your strong suit, and if that question make you recoil like it did for me, you can also ask another version of that question, which is what is easy for you? Perhaps what is easy for you is not easy for other people. And then that would be likely your strong suit that you can develop into your expertise. And then if you know who you are and what you can bring to the world that is very special, you don't have to worry about whether you will make it, because you will make the path. You will open the path. Thank you for your attention, and I'll be happy to take questions.
So thank you so much, Professor Kim, for the amazing talk to your speaker today. So now we are moving on to the Q&A session between the speaker and the audience. So as Tom explained in the beginning of today's event, please raise your hand in the Zoom participant sidebar and we can call you, or you can also privately send a message to me and I'll ask the question for you. So we want to make Chilloquium feel as conversational as we can, so we will prioritize the ones who raise their hand generally. So yeah, let's start. So do anyone have questions?
While the audience is like thinking about the question, I actually have one question to Professor Kim. So like I learned today that like a lot of your research is in the interface between like theory and experiment, basically like using the theoretical analysis with data and all those stuff. So I wonder whether those kind of like character of your research is originated from your education or your training as well. Like for example, when you are in your like master's degree or like PhD degree, did you also do like those kind of work that is like in the interface between theory and experiment, or did you shift towards those kind of style of work as your career like progressed?
So I during my master's in undergrad, the culture of my university was that there wasn't a lot of collaboration between theory and experiments. But I was interested in, I liked theory, I liked making stories, but I wanted my stories to be grounded on reality. It was just an innate desire. Somewhere when I was even younger, I debated about what scale I wanted to study. I knew I wanted to be a scientist, and I debated about what scale I wanted to study. Astrophysics seemed to take it takes a long time to study. And high energy physics seem to require instruments that involve large number of people and also big time investment. I am not a very patient person. I don't have strong patience, not my strong suit. So I wanted to know whether stories that I'm making up had any grounds to stand on, any legs to stand on right now, tomorrow at most, or maybe a month, maybe a year, but not 20 years from now. So that was just something that was important for me. I always liked math, but when I decided I decided that I like science better because there is connection between reality and theory, and that experiments can always be a check. So that was something that was important for me. I didn't have opportunities during my master's. When I went to do a PhD, because that was what was important for me, I was looking from that angle. My PhD advisor, Eduardo Fraken, is his style of research is much more formal than my style of research at this point. But he still very much cared about experiments. And with edge states, quantum Hall edge states, that was special to me because edge states give you the window into the system that can connect conformal field theory to experiments. So I think it is more reflection of who I am. But because this was important to me, I was looking for such opportunities, and that was a direction that I have taken my research. that's also why I wanted to do postdoc with Steve Kibbleson, who is an amazing phenomenologist, and he has a really sharp angle into looking at experiments.
Oh, I see. Thank you so much for sharing your wisdom. That was really great answer. Thank you so much.
Right, so does anyone else have any questions for Professor Kim?
I have a question actually. Thank you so much for the wonderful presentation. You said things about like figuring out what's easy for you. When were you able to figure out what was specifically easy for you, and how did you figure that out?
So yeah, when was that? I think around the time when I was on my first sabbatical, pretty late, right? So I had two kids. I had two babies while I was an assistant professor. And each baby takes up about 3 years, so solidly. I mean, children are amazing, but also a lot of work, especially during first 3 years of their lives. So by the time my second one was 3, that's when I was on my first sabbatical, I had a little more room to breathe. And I was having a conversation with my husband, who's also a physicist. He's also a condensed matter theorist. And he was asking me, like, how do you do X? I'm not going to tell you what X is, but he was asking me, how do you do X? And I'm like, it's obvious. Like, isn't that obvious to you? I mean, can't you just see it? Isn't it obvious? And he said, no. And I'm like, what? So that's when I realized what is obvious to me is not obvious to everybody. So some of the things that come very easy for me is understanding what other people care. And it's not clear to you, it's not obvious to everyone. It may not be obvious, that's important, but it matters, because when you know what somebody cares, that forms the entry point of conversation. That forms the entry point of collaboration. I love to collaborate with people. I love working with people, and the process of making 1 + 1 much greater than 2. That's something that I love doing. And I probably love doing that because I'm good at it. So it took me a long time. And I wish somebody told me that that's a way to find what you're good at. I didn't know what I was good at. And I probably was really lucky to have made that far without knowing what I'm good at. So if you didn't know this until now, you're far from being late. But this is what I tell my students, right? Because especially when jobs kind of comes in front of your eyes, some application time, you're graduating, you're going to a graduate school, you have to write your research statement, you're going for a postdoc job. Each time you have to apply for something, people ask, why should they invest in you? That's what all application process is about. So the anticipation is you will tell people what you're good at. And I didn't know how to say that. So now I do. Now I know how to say what I'm good at, because I can translate that question into talking about what is easy for me.
Thank you so much.
All right, so it looks like we are nearing the end of our time. For those of us who are joining us for the first time today, so please sign up to our Chilloquium mailing list that we just posted in the chat. And we send out a weekly email about the upcoming Chilloquium talk and a reminder of the day of the event through this mailing list. So if you want to stay updated on what talks are coming up, please join the list. So thank you so much again, Professor Kim, for a wonderful talk today. And we'll see everyone in 2 weeks. in Professor Francis Hayton's Chilloquium talk on July 31st. Thank you and goodbye.
Thank you.